In this video, we're going to have a look at questions based on the ideal gas equation. And the main part of this video is really to help you spot literally a mile away where these questions are because they're massively telegraphed in exams. You can see them literally as soon as you read the question, you should be able to spot that this is ideal gas, and this is how I need to work them out. So main issue with ideal gas is mainly the equations required and typically the conversions that are needed. So I'm not going to go through the whole thing in detail because obviously this is something that you can just learn. But whenever you see a question like this, okay, so let's just run through the one I've got. You're given a volume, that's pretty standard. An amount in kilograms, that's not always standard. But then the key, the giveaway, as it were, that this is an ideal gas equation question is the fact that they give you a specific pressure and temperature as well. So they've given you a volume, a pressure, and a temperature, and they want you to work out the molar mass. So the actual ideal gas equation is PV equals nRT. Okay, where P is the pressure, V is volume, N is moles, R is a constant, the gas constant, and T is temperature. So the whole point of this question is effectively, in order for them to in order for them to use the ideal gas equation, they have to give you at least three numbers, okay? Because R is given, so they must give you P, V, N, T. They must give you 3 out of 4 of those in order to work out the remaining one. So there are many variations of the ideal gas equation. Of course, you can rearrange this to solve for any of the values. So you can solve for P, V, N, R, or T. You'll never need to solve for R because R is a constant. We know what that is. We just want to quickly run through a quick reminder then of what the units are for these quantities. So pressure is always in pascals. Volume is a bit of a strange one. It's in meters cubed, something we don't see very often. N is obviously in moles, that doesn't change. And T is in Kelvin. Now, R doesn't matter because R has its own units, it's a constant. And this, in fact, this is the reason why pressure, volume, moles, and temperature have to be in these units. It's to satisfy the constant R, which we can't change. So these are the units we need for our ideal gas equation. The next part is about figuring out how to use it. So let's take this question, for example. The question is asking us to determine the molar mass of an unknown substance and identify the gas. The identifying the gas is the last bit at the end. We're not really interested in that for the time being. The trick is we want to work out the molar mass. So in order to determine the molar mass, we need to look at our ideal gas equation and determine which of these quantities we need. Now, we are given a fair few in the question, which narrows it down substantially. So we know that if we want to work out the molar mass of something, we need the moles, okay, and we need the mass, okay. So, how we'll do this: molar mass equals, mass over moles. That's a straightforward equation. We're given the mass. Mass is in the question there. It's 1.69 kilograms of the gas. The moles is what we don't know, and that's part of the ideal gas equation. But we are given pressure in pascals, 1.37 times 10 to the 7, volume 9.39 decimeters cubed, and temperature 20 Celsius. So all we need to do then is rearrange the ideal gas equation to solve for the number of moles. And the way I'm going to do this, I'm going to get rid of this little circle here. The way I'm going to do this is by taking my value for RT and pushing it to the other side of the equation. So if you don't know how to rearrange equations, this is something that you really should, obviously need to practice. But for PV equals nRT, you can just learn the correct equations. You don't have to rearrange every time. You can just learn them. So I know that because I'm dividing by RT on both sides, N is going to be equal to PV over RT. So all we've got to do now is plug in the numbers and make sure that they stick to the correct units. So P is first. P needs to be in pascals, and it is in pascals, so I can leave it like that. 1.37 times 10 to the 7. Now, volume needs to be in meters cubed, and I'm given a value in decimeters cubed, so we're going to have to convert it. Now, there are 10 decimeters in a meter, so you may expect that you're going to need to divide by 10 here. However, it's a cubed term. It's decimeters cubed, not just decimeters. If it was decimeters to meters, just divide by 10, but it's cubed. So you have to do a decimeter cubed to a meter cubed, and that is basically, if a decimeter is, if you can have 10 decimeters per meter, then you'll have 10 times 10 times 10 decimeters in a cubic meter. So that means 1,000. So in order to convert from decimeters cubed, okay, to meters cubed, meter cubed being the, is a, it's a smaller quantity, it's a smaller quantity because it's a larger unit, I'm going to have to divide by 1,000. Okay, very similar as if I was going from centimeters to decimeters. Okay, it's the same process. Okay, you can actually link these together. Okay, from our work on concentrations and volumes, when you do concentration calculations in titrations, it's a very, very common conversion. Centimeters to decimeters is divided by 1,000 because, again, there are 10 centimeters in a decimeter and you're cubing that, so 10 times 10 times 10 is 1,000. And that means, this might be useful later, if we want to go from centimeters cubed to meters cubed, we have to do divide by 1,000, divide by 1,000. So you have to divide by 1 million. And the same works the other way. If you want to go back the other way, just multiply by 1,000, multiply by 1,000. The upshot is the conversion from decimeters to meters cubed, decimeters cubed to meters cubed, is divided by 1,000. So we take 9.39, divide it by 1,000, and we plug that number in, so 0.00939. And then we divide that by the gas constant, 8.314, multiplied by the temperature. Now again, the temperature is given in Celsius and will almost always be given in Celsius. You have to remember the standard conversion here is to add 273. So that gives me 293. And then we simply have to work that out on our calculator. So just be careful when putting this into the calculator. It's very easy to make a slip, I suppose, with the calculator. Transcription errors are very, very common and will cost you marks in the exam. So it is important to make sure you get it right. Okay, always double check your working out as well. If you've done it once on the calculator, do it again, make sure you get the same answer. So that gives me 52.809069994 moles. Now I've put the whole number down here. I wouldn't normally do that, but what I would say is don't round it. Okay, we don't round any numbers until the very end, so leave it on your calculator as it is. 52.8 blah 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 is our number of moles. We now need to plug that into our molar mass equation because that's the number of moles. And we need the mass over the moles. So the moles is on the bottom, that's 52.809 blah blah blah. And the mass is up here, 1.69 kilograms. We need that in grams. So that's 1,690 grams. So 1690 over the answer gives us exactly 32. Well, 32.0020, but yeah, 32 is the answer. And therefore, it says it's an unknown gas. You need to think of a gas that might have a molar mass of 32. There's a very, very common one that, most people should be aware of, I would hope now. Oxygen. Okay, so oxygen is a gas and is a molar mass of 32. There aren't really many other options, if I'm being honest. I mean, if you're getting the odd trick that people might fall for is putting sulfur instead. Now, sulfur isn't a gas at 20 degrees Celsius, so it can't be sulfur. Sulfur's a solid at room temperature, so it's definitely going to be a solid at 20 degrees Celsius. There aren't really any other common gases you'd have heard of that have a molar mass of 32. Whenever you see 32 and it's a gas, it's almost always oxygen. Just a bit of exam technique there, just to remind you. Some things you can just learn. They come up very often, and it's always good if you can recall them. So that's the first question. Then I'm just going to show you then another question based on this. So again, alcohol A contains carbon, hydrogen, oxygen. It's a liquid at room temperature, easily vaporized. And once again, reading through the question, this is how you spot them a mile away. We've got a mass of A producing a certain amount of gas measured at a temperature and a pressure, or pressure and temperature, I should say. Again, this is screaming ideal gas because you're given so many numbers and one of them is pressure. And pressure is a really weird number to be given in a chemistry exam. So it's almost always ideal gas, unless it's a question based on KP, which is a second year concept. It's really obvious though. This is really obvious that it's a PV equals nRT. And again, we're working out the molar mass. So same principle as last time. So I'm not going to go through the ins and outs of the rearrangement again. N is PV over RT. We're going to do exactly what we did before. This time, however, we have something slightly different. We have kilopascals instead of pascals. So 1 kPa, just as a quick conversion reminder, is 1,000 pascals. A bit like a kilogram is 1,000 grams. A kilopascal is 1,000 pascals. You need to convert to pascal, so just times by 1,000. So you've got 100,000 pascals multiplied by the volume. Again, weird volume here. This time it's in centimeters cubed. They will give it you in centimeters cubed occasionally. You have to get it into meters cubed. They do this to test whether you can do conversions. If you recall what I said earlier, to get from centimeters cubed to decimeters cubed, you divide by 1,000. To get from decimeters cubed to meters cubed, divide by 1,000 again. So we're going to divide by 1,000,000. And that's going to give us 0. Oh, God knows. Hang on. I say this. I can do it in my head, but I don't want to make a mistake. Yeah, so 1, 2, 3. There we go. Just have to do it in my head. Yeah. Don't want to make a mistake again. Even if you think you can do it in your head, just double check it. There's no reason to make a mistake on this. I see too many students making mistakes with transcription errors and not putting the right number of zeros or switching two numbers around. It happens way more often than you think. Always double check. Bottom half then, 8.314. Okay, that's the gas constant multiplied by the temperature. This time the temperature is in Kelvin, so we don't need to convert it. Again, it does depend. Really does depend on the question. Sometimes you'll have lots of things to convert. Sometimes you'll have basically nothing to convert. So, just be prepared to convert everything, even though you might not have to convert anything at all. So that gives us 0.02500 something something something. I'll leave that on the calculator. That's the number of moles. And then to work out the molar mass, we do exactly what we did before. 1.15, which is the grams in the question, by the way. That's where I've got that number from. It's the grams of A divided by the moles that I just got, 0.025, blah, 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 blah. Again, I'm not rounding. I am just putting it on I'm just leaving it on the calculator. I'm just not writing all the numbers down because I don't want to. And that gives us a mass of 46. Okay, so at that point then you can figure out what the alcohol is. So with a molar mass of 46, I will just show you. Okay, so an alcohol is a straightforward functional group. Because the molar mass of 40 is only 46, it's actually very straightforward to work out because it can only be so many things, and in fact, it obviously can only be one thing. But when you've got a small molar mass, you might be scratching your head, but just trial and error. Okay, it really is trial and error because with such a small molar mass, it limits the options massively. If I start with the simplest possible alcohol, let's just start with methanol. So if I just draw methanol out, okay, so I've got 12 for carbon, 16 for oxygen makes 28, 29, 30, I've got, then that's 32. Okay, so it's not that one, but you can see where this is going, I'm sure by now. If I do the next most straightforward alcohol, which is ethanol, put my hydrogens on, I've got 12, 24, oxygen is 16, makes 40, and 1, 2, 3, 4, 5, 6 is 46. So it's ethanol. Again, you can do it. You can just work it out by subtracting the oxygen, finding out you've got 29 left over, and then working out that means it must be a CH3, CH2. But because it's so small, you can just trial and error it. If this was over 100, then you're going to have to. Yeah, but again, even if it's over 100, you can just start with 4 carbons or 5 carbons. You can limit your options very, very quickly because it's an alcohol because it tells you in the question it's an alcohol, and because it just says alcohol, you can make the assumption that it's not any more complicated than that. It's just an alcohol. There's no tricks going on here. And again, there's only one structure it can be, so therefore it's ethanol. So hopefully then, this has been helpful, just spotting how you can figure out whether a question requires the ideal gas law And then the most important thing for picking up marks in these scenarios is doing your conversions correctly, rearranging the ideal gas equation correctly. And again, you can just memorize it. There's only 4 variations that you'll possibly need. That's for solving for N, P, R, sorry, N, P, V, or T. R is not required to be solved for. And once you've done that, it's just about putting the numbers in and then using your answer to work out whatever they're asking for. So the common distractor in these types of questions is the number of grams at the beginning. So this number here, because people think that they need to put that into the ideal gas equation. Not every number they give you will need to go in there. Okay, sometimes the numbers they give you are used later on. So in this case, I have to work out the moles so that I can use the mass to work out the MR. Okay, it's nothing to do with the ideal gas equation. But if you can get this, into your head, if you can just do these questions, quickly and accurately without really thinking too hard, you can pick up absolutely loads and loads of marks because the questions are very much the same. They can't really ask many variations of this. And that means that, once you've got this in your head and, you can do this, confidently, you'll be picking up, 5 out of 5 every time you see one of these questions.